Hello.
Yes,
Sir, I have a doubt on bias and variance. May I ask the question now, please?
yes, you can ask.
Suppose we have some data points, actual values and predict values, like array of values. So how to evaluate that bias and variance, sir? In the normal classes, we have gone through some equations. If we substitute, we have a bit doubt in differentiating the bias with the variance.
Okay,
Can
so
you add?
variance is basically what you basically calculate the variance. Am I audible? I think my internet is somewhat that
In
great.
between,
Let me
voice
check.
is becoming very low, sir.
Oh, am I audible now?
Yes, sir. Now it is okay.
Okay. So generally, in case of variance calculation, let's say you have the true values and as well as you have got some predicted values from the what you call the model. In general, DL model, ML model, whatever architecture that you have some predicted outputs. So variance is basically calculated on the predicted values. So it uh, I think I have started recording as well. Yeah. So it is basically calculated on the predicted values. So variance of, let's say your your original values are basically labeled as Y, and you predicted the predicted results are basically annotated as Y hat. So
Yes.
variance, you basically calculate variance in Y hat. So variance is Y hat basically means expectation of Y hat ka whole square minus expectation of Y square. Okay. So this is normal, like you consider that your output basically follows the Gaussian distribution, and then you have the formulas for that, and then you can calculate the value, or you can calculate the variance.
Last
Otherwise,
year, we have tried on
yes,
one
yes.
problem. Sir, can I give the value so that we can verify? We'll get more clarity on that if we solve it for us.
Okay, so what you can do is basically you can there is a Q&A, but Q&A section is there, right? In the course website. So in the course website, let me just show you once if you don't know. Uh, I think my screen is visible as well.
Yes, sir.
Uh, okay, so let me go to course website. So you can go to this Q&A section, and then you can post a new conversation, and over here you can post all these values. Okay, so you post the whole question, so I will solve it and I will reply to that particular question itself, so that you will get bit insight on the values, because otherwise over here sharing the values would be quite cumbersome. So you can post the whole question over here, otherwise you can put a screenshot of the question as well, and then I will solve it and send it to you. Is
Okay,
that
sir.
okay?
Okay, sir. Okay, sir. Thank you. Thank you.
Okay, so I think now we can formally start the session. Yeah. Okay, so good evening, everyone, and welcome to this week 2 live session on NPTEL course titled as Machine Learning, Deep Learning, Fundamentals and Application. So this course is provided by Professor M.K. Bhuyan, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Guwahati. So in this particular live session, the plan is basically as what I think is basically this machine learning, deep learning course. These are quite applied courses. So just learning the theoretical part is not enough if you think in terms of particularly applying these concepts in real life applications. So if you want to employ these concepts that you are learning in the theory classes, if you are trying to use it in, let's say, if you are doing some sort of research in this particular area, or you are trying to, let's say you are a developer as well, you are a MLDL developer as well. So over there, you need to implement these algorithms on different environments. Let's say if you are a developer in Python, so you'll be employing these concepts and try to implementing it on Python. Otherwise, if you are working on MATLAB, so you have to implement in MATLAB. If you are working in R, so there are n number of languages. At the same time, if you choose Python, you'll see there are several distributions for machine learning and deep learning applications. So it basically the quite naive applications could be on scikit-learn, the advanced applications that you'll see in TensorFlow, Keras, and in Pytorch as well. So one of the two most popular distributions that we use nowadays, these are TensorFlow and Pytorch. So TensorFlow is quite like, if you know MATLAB, so you'll see that in TensorFlow, you can write the codes in sequential format, or it's like a sequence by sequence format, you can write it. Otherwise, if you see predominantly in PyTorch, you'll see that there is a concept of object-oriented programming. OOP kind of structures are there. So you'll see while writing the codes, I may infer to class, then super declaration of the supers, init, etc., etc. But don't get intimated with all these terminologies. So I will later on explain that what is basically the aim of today's classes. So uh, in week 2, you have seen that Professor M.K. Bhuyan has given a lecture on Bayesian minimum error classifier, disk classifier, and discriminant function predominantly. So, and the Bayesian belief network. So this is a very glimpse of the idea of Bayesian belief network. So if you are not able to understand this Bayesian belief network currently, I would recommend you to wait for some time. Probably in week 4, you'll see that the same concept will be taught in a bit detail in hidden Markov models. So this is very glimpse part of the Bayesian belief network. Later on, you'll see the main applications as well as the main theoretical development over there. So if you're not getting the point currently, so there is no need to worry. Just wait for week 4 or something. So then you'll see that total theoretical development over there. But predominantly in this particular week, we have focused on minimum error classifier, risk classifier, as well as the discriminant functions. So these comes under the hood of statistical machine learning. So over there, you try to learn from the data and try to create some rules, or the decision boundary is basically made upon some sort of weights and biases that you learn from the statistical property of the data. So why I'm basically referring to the statistical machine learning or statistical property of the data. So in all the derivations, you've seen that predominantly you think or you assume that the data is basically coming from a Gaussian IID. So or a Gaussian distribution, so to say. So for Gaussian distribution, you have the equation of the probability density function, both in the univariate case and multivariate case. And in machine learning, deep learning, you'll see majority of the applications is basically based on the multivariate case only. Because if I give you a very naive example, so it could be a, let's say, a cat and dog classification. So for cat and dog classification, only relying upon on a single feature, let's say you want to rely upon the length of the tail for cat and dog. So this length of the tail, if you are relying upon on a single feature, that would not be enough to get a good classification accuracy, because this may introduce some sort of a it may introduce some sort of a confusion over there while you do the classification job. So rather, what we use is basically we try to use different sort of uh, uh, features. We extract different sort of features from the images. Let's say texture based features, then the energy based features, the RMS values. There could be n number of features, and then we use all these features to do the classification job. So therefore, instead of relying on a 1D feature, we are relying on a D-dimensional feature, and that is why when the D-dimensional concept is basically coming, so that means you have multiple amount of dimension, and that is why the probability density function also shoots up to from a univariate case to multivariate case. Fine. Now, after that, you have seen that in case of discriminant function, there could be three scenarios. One is basically based on the covariance matrices. One could be the matrices are the features are independent of each other, or statistically they are not correlated. So, and all the features are basically having the same variances. So over there, the sigma, the capital sigma is basically small sigma squared into I. So that case, you have seen that if you have two clusters and the decision boundary will be a orthogonal or a perpendicular bisector. Bisector of the lines joining the two means. If I just show you in terms of mathematical interpretation, yeah. So there were three cases. One was basically, so this sigma I is equals to sigma square into I, and which is same for all the classes. So over there, so this has a quite pretty well interpretation that if I just expand it, it would be sigma square, dot, 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 sigma square, and all other off diagonal elements are null. So that is why I'm putting a big zero over there. So can anyone tell me that what statistical independence basically mean, or orthogonality basically means? With example, do you have any sort of example by which you can actually think of that what basically means the orthogonality or the independent features or something like that? But how to know two features are orthogonal to each other? Let us start with a very basic question. How to
Their
know
inner
that
product should be 0.
their inner product should be 0? Yes. So let's say you have A as a feature, and in the last class also, feature basically, last class also I told that feature you can represent it in a vector space as well. So A could be a feature and B could be another feature, and A and B equals A and B ka dot product. If it is equals to 0, that means inner product is equals to 0. That means they are orthogonal to each other. So over here, if I just expand this particular thing again, so you have x1 feature, you have x2 feature, let's say you have xn feature. And correlation or the covariance is basically calculated like this: x1 feature, x2 feature, dot, 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 xn feature. So you first calculate the covariance between x1 and x1. So it would give you sigma 1, 1. Similarly, it would give you sigma 1, 2. And likewise, it would give you sigma 1n. So this would give you sigma nn. Now we know that sigma 1, 1 is basically means that expectation of x minus mu multiplied with x minus mu. So I can write it as expectation of x minus mu square. So that means it is nothing but the variance. So sigma 1 square. So all these 1, 1 terms or the identical terms will be converted to like this one only: sigma square, sigma square, sigma square with their proper subscripts. Now, this particular thing is basically the correlation between feature 1 and feature 2. So this is something you can intuitively understand that you are doing something like this. That means x1 dot x2 dot. Okay, now over here, this case is the off diagonal elements are 0. So over here, this means this x1 and x2 dot, the inner product is 0. So this is orthogonal to each other. Can you give me any example that two vectors which are orthogonal to each other and independent of each other? Very basic example. You don't have to think about big vectors or something. Very basic example you can take. Okay, so the very basic example could be to show that the independence or the orthogonality. So orthogonality and the independence, so to say the statistical independence, I will show you through this particular example. So we all know Cartesian coordinates. In case of Cartesian coordinate, let me consider we have a two-dimensional coordinate system. So the basis functions for the coordinate system is basically for x direction you have I cap and y direction you have j cap. So this particular product also means that angle between these two, that means the argument or the argument between x1 and x2 is 90 degree. This inner product 0 also infers to this condition because cos 90. So from there, you know that that is why you are getting the 0 value. So in case of this particular direction, in the x direction, you have I cap, in the y direction, you have j cap. These are the unit vectors along these Cartesian coordinates. Now, if you do the inner product in between them, what would be the output?
0, sir.
Yeah, so you'll get 0. So this is the example of orthogonal vectors. Now, how come you can infer something like independence or they are independent of each other? How we can infer to that particular logic? Orthogonality is okay because mathematically we can see that I cap dot j cap is equals to 0 as because they are having a phase difference of 90 degree. Now, the thing is that how we can interpret that they are independent of each other. So you can see that only when these two axes are 90, these two axes are 90 degree apart, then if you have to traverse along only this particular x-axis, let's say you have to only traverse along x-axis. So let's say you want to go to 3 I cap. So over there, if you have to go to 3 I cap, so you don't think about the j cap, you don't bother about the j cap, as if there is no relation that if you only walk, if there is a person in this particular axis, if he is basically walking on this particular pathway, and you'll see that if he has to go to 3 units ahead, so you don't bother about the contribution in the y-axis. You just go straight along in the x-axis only. Similarly, if there is another person in this particular direction, so if he has to go to, let's say, 5 j cap, so you don't think about I cap component. So this I can rewrite it as 0 into I cap, and over here I can write it as 0 into j cap. So why I am telling this, because this may seem to that this is pretty nice that if I have to go around x-axis, I will only be bothering about the I cap only. If I have to go in the y-axis, I will only be bothering about j cap only. Now let me give you another sort of axis distribution. So let's say you have an axis like this, and the second axis is looking like this. Now they are not orthogonal to each other. The axes are not orthogonal to each other. And let's say this is I cap, and let's say this is M cap. The unit vector along this particular direction is I cap. The unit vector along this particular axis is M cap. So over there, if you move along this particular axis, so you may see that you are going to 3 I cap. And let's say the angle is, let's say, 30 degree. So you can go to 3 I cap. So will there be another component? If you go to 3 I cap, will there be another component in this particular axis too? Due to movement of 3 I cap, will there be another component on this another axis? Yes, anyone? Yeah, so I was telling that now the axis instead of having 90-degree phase difference in between two axes, now you have a phase difference of 30 degree. And let's say you are moving along this particular axis to 3 units. So therefore you went to 3 I cap. Now if you have moved to 3 I cap, will there be any effect in this particular axis, in this axis number 2? Due to movement to 3 I cap, will there be any effect in the other axis or not? I mean, are you able to relate to any sort of vector algebra concept? So,
So there won't be no change
so there will be no change.
because the magnitude in the y-axis component is 0.
Yeah, uh, apparently it seems like the magnitude in y-axis, y component is 0, but
Since
there
we say,
would
sir,
be,
a dot b is 0 means, since we
yeah,
say a dot b is 0 when with two conditions that maybe the magnitude is 0 or the angle between them is 90-degree. So
so
based on that, I'm
let us
saying, sir.
consider now. Let us consider cos of theta. So this is a dot b. So this is for a dot b. Now I am asking that if you have only a cap, I am not asking you to do a dot but a dot b cap, because you don't have any b cap component as such. So the question is, if you just move to this particular axis, will there be any sort of component in the y-axis? So he said that there is no b cap component, as because I am not moving in the axis number 2. But there, as if it seems that there is no component, but there is actually some contribution will be there. So that is called vector projection. So I hope that you know what is vector projection. So it is like you have a vector like this, you have another vector like this. Let's say this is uh, uh, V1 and this is V2. So projection basically means the V1 cos theta. So this you have studied in your +2 level vector algebra as well. So this is called vector projection. So this thing over here, it was not there. Why it was not there? Let's say you have a V1 component over here when you are residing in the X direction only. So over there you have 3 I cap. So the projection of this particular vector into this axis would be 3 I cap into cos theta. So that is cos 90 degree. So that is why you get 0 into I cap. So over there, that is why you do not actually bother about the x component while going into the y axis. And that is why you'll see whatever coordinate system you took, let's say the Cartesian coordinate, let's say the cylindrical coordinate system. If you are from the electrical engineering background, so you have seen all these coordinate systems. So everywhere the basis function or the coordinates, the directions of these coordinates, they are basically perpendicular to each other. Even if you increase the coordinate, let's say from 2-dimensional to 3-dimensional, you'll see all the coordinates are basically 90 degree apart from each other. So in most of the cases, you'll see that the coordinate systems are basically considered in a 90 degree phase or 90 degree apart kind of system, such that you do not basically think about the correlation when you move to the x-axis or when you move to the y-axis, or if you move to the other axes as well. Had it been the case like you are taking the axis like this sort of where they have dependency on each other, so even if you move to I cap or you move to the axis number 1, apparently it seems that there is no sort of effect on the other axis. You see that you can get another component in this direction as well. So that is basically it is called. So this particular area will be called the vector projection. And if you take features like this, which have correlation with each other, x1 and x2. So now you can see as they have correlation with each other, and let's say x2 belonging to class omega 2 and x1 belonging to class omega 1. In machine learning problems, the machine learning classifier will be happy to classify those particular features which are uncorrelated. What do I mean by uncorrelated? If you can think of a feature, let's say you have extracted features. Let's say this is x1 feature from class 1 and this is x2 feature from class 2. So the uncorrelated feature will look like this. They have no correlation. Rather, if you take the feature like this, which have correlation with each other, so you will see the feature from x2 will look like this. So that means they are overlapping with each other. Overlapping means they are containing some sort of similar kind of information. They have something like common in nature. So we don't want those types of features. So this is what basically statistical independence means. So in the subsequent lectures, there will be a lecture series on principal component analysis, PCA. So over there, you'll see that you basically try to employ this particular concept. You have some sort of feature dependency or correlation, and through some mathematical formulation, you try to extract those features which are uncorrelated with each other. So so for this particular case, you have seen that the if your clusters are like this is for omega 1 and this is for omega 2, and these are the means of the clouds mu1 and mu2. So the decision boundary would be, this is the line joining mu1 minus mu2, and the decision boundary will pass through the middle point of this mu1 minus mu2. So this is called, and this will be orthogonal to each other. So this is 90 degree. So this you can get from the mathematical formulation. So there are two other cases. So over there, the second case is basically sigmas are same, but these variances are different. These variances are different. So over there also you get a perpendicular line, perpendicular decision boundary, but that is not that is not actually the perpendicular to mu1 minus mu2. So there is a component like it capital sigma minus 1, mu1 minus mu2. So these formulas that you have to remember for the final exam. as because the exam will be MCQ or something like that. But my suggestion would be whenever you see some sort of formulation, you try to think in terms of physical interpretation of those equations. So something like feature independence or correlation, because you see that in this particular coordinate system is totally based on this statistical independence. You choose this particular coordinate system due to some sort of advantages. When you have statistically correlated, uncorrelated system, so then you don't have to think about when you go along this particular direction, you don't have to think about the I cap, the J cap. And when you go along this particular direction, you don't have to think about I cap. So these kind of intuitive understanding is quite important. So that is what I want to bring this point over here. Okay. So in this particular class, what I had planned is basically we'll be doing some sort of simulation. So I will basically try to give you a glimpse overview about the machine learning, the very basic machine learning data sets. So we will be using so we will be using TensorFlow as well as Pytorch, and we'll see two different data sets. One is MNIST data set. So MNIST dataset is basically our handwritten digit dataset. So it basically comprises the images of 0, 1, 2, up to 9. And the images and the challenge over here is basically how to, given these images, how to classify that the image belongs to 0 or image belongs to 1 or image belongs to class 9 till that. There is another data set that is called CIFAR10. So this CIFAR10 is a data set of images of objects. So there are total 10 number of classes are there, like images of bus, truck, frog, horses, etc., etc. So there are total 10 classes. Then I will tell you about feature extraction. Feature extraction. So feature extraction itself is a very vast domain. So just to acquainted with that how to extract features from images, I have taken two different sort of images. One is local binary pattern, and one is another one is filter based features. So we'll extract all those things in Python itself. We'll be using sklearn library, scikit-learn library to extract features. Otherwise, so these are the standard techniques. I'm not going into something advanced. So these are the standard image-based features. You can see any sort of image feature extraction techniques. You'll get n number of contents out there in YouTube or in the web as well. However, I have taken only two features. And then you have read about the naive Bayes classifier in this particular week. So we'll be using the Gaussian naive Bayes classifier to classify. And at the same time, as because in the previous class as well, I saw that many of the participants are also doing research in biomedical signal processing or like leaf disease classification and other things. So I thought of considering another example of ECG classification. So in case of ECG classification, we'll be trying to classify the abnormal bits in the ECG signal. So I request you all to have a Colab account. So this is Google Colab. In case of Google Colab, you don't have to install anything into your particular laptop or desktop. So everything will be on the web itself. So Colab also gives you the power of GPU as well. So in other platforms like Kaggle and all, you'll see the CPU. Currently, Kaggle also provides some sort of GPU, but in case of Google Colab, there are several sort of GPUs available like A100, V100. So this basically helps you to brought down the computation complexity at quite ease. If you have bigger models, you'll be able to you will be able to do the computations over there. And this is a web-based application. So if I just go to the so you start Colab. So when you open Colab, something like this will come. This sort of interface will come. Then you have to log in into your Gmail account. So for this particular class, so now when you will be starting with Colab, there is a tab called New Notebook. So you can click on New Notebook. So it will open Python environment for you. So over there, you can start writing code. So already I have written down some codes for you. So let me just open that one. Okay, so this code I will also be uploading in my GitHub profile. So you can directly download that code from there and you can also run it in your Colab account. Otherwise, what I will do, I will put a bar over here. So from there as well, you can just, if you click on that particular button, it will directly take you to Colab. Okay. So here the dataset information is also provided like CIFAR10. It is a image dataset. So there are 60,000 images and the images shape are 32 by 32. And these are colored images. So in case of colored images, how many channels are there? Yes, anyone? In case of colored images, how many channels do we have?
3, sir.
Yeah, so we have 3 channels, RGB. So red, green, and blue channels are there. So that is why these are colored images. And the other one, the MNIST is basically a grayscale image. The grayscale image basically means that as far as the number of channels is being concerned, so it has only single channel. It is not a 3-channel image. So that is why you'll see there is no color in that particular image. And the intensity levels are basically distributed from 0 to 255. So let us start discussing what we have written over here. So import PIL. So there is a library called Pillow. So this particular library basically helps you to handle the images. So there is another library that I have imported. So this is called TQDM. So I'll show that why TQDM is basically used over here. Then we have import pickle. So pickle is basically a library by which you can store the data. Let's say you have extracted n number of features, and if you want to store that data, so you can use pickle library. You can store that data and you can download that particular file as well using pickle library. Then I have used NumPy as NP. So NumPy is basically the library that I am referring to. So this particular NumPy basically helps you to do the array operations and other kind of stuffs on the array. Basic array operations can be done using NumPy. And I am renaming it as NP so that I don't have to write NumPy again and again. So I can write NP as well. So to visualize the data, we need to plot the data. And how to plot the data? So to plot the data, we can use this particular library. So this is called matplotlib.pyplot. And then we have a famous distribution for deep learning, machine learning application, that is Torch. So that is why I have imported Torch. And to access the state-of-the-art data sets or to access the existing data sets. So because this application is on images, because we have seen that CIFAR10 on MNIST, these are the image data sets. So all the image data sets are basically stored in Torch Vision package. So from Torch Vision, I'm importing the data sets. So this is like, if I just show it in the slide, you have Torch. So this is the bigger bucket, Torch. In Torch, there are several sub packages. Like this is called Torch Vision. So Torch Vision only deals with computer vision related problem, or so to say, image related problem. There are other things like layer based libraries and all. So inside Torch Vision, you'll see there is another sub folder. So that is called dataset. So inside this dataset, you will see even smaller folders like CIFAR10. Then you can find MNIST. Then you can also find something called petal datasets as well. So those basically contains the images of flowers and all. So there are n number of datasets that you can also look into. So you can run it from here. So when you'll run, you'll see that on this particular site, if I just zoom it a bit. Okay. So over here, if I just run this, you see that over here, it is now connecting with the web. So when it is basically connected, if you just see, it gives you the RAM space of 12.7 GB, a disk space of 107 GB. So it is a pretty huge disk size. So you can upload big data sets as well. Obviously, it should not exceed this particular memory amount. Otherwise, you'll not be able to store the data sets. Okay. So what I was asking, what I was telling is that TQDM, why I need TQDM. So let's say you are running an epoch and that epoch is will run for, let's say, 1,000 instances. So you have to wait for epoch number 1 to epoch number 1,000. So the TQDM basically shows you the progression of the loop. So whether it is 50% completed, 70% completed, something like that. So over here, I have just written like for I in TQDM range 20, that means this particular loop will run from instance 0 to 20. And using TQDM will give you the visualization that what is the current status of this particular loop, whether it is 10% completed, 20% completed, or 100% completed. So this is just to see that what is the progression of the loop. So over here, you can see that it gives you the progression of the loop. Nothing fancy. Now, the thing is that how you can import the dataset using Pytorch. So over here, we'll be importing the dataset CIFAR10 using Pytorch. So over here, there are two folders in any sort of dataset. You'll see there are two folders. One is basically the train dataset. Another is basically test dataset. If you don't have the splitted folders like train and test, then you have to do it by yourself. There are certain mechanisms are there, certain functions are there. You can employ those and you can do this particular thing. But in majority of the cases, it is pretty standard that in the dataset folder, you'll see there are two subfolders. One is train and one is test. So you can import those using datasets. We have already loaded datasets from Torch Vision, and we can write TensorFlow. And I want to extract the train folder only. So I can write it is true and I want to download that folder. So that is why I have written download true. Same for the test part as well. So if I just run this. Yeah, so it has downloaded them. Now it is extracting. So it is downloaded and verified. So if I just show you over here, so you can see that the CIFAR10 dataset has been downloaded. And if I just open it, so it basically gives you the compressed file from which it can also basically extract the original files. And you can see the data structures as well. So it has extracted in different batches, let's say batch 1 to batch 5. So which is not quite important as of now. And the thing is that in case of CIFAR10, as we have already discussed, the CIFAR10 dataset comprises 60,000 images. In the training folder, you have 50,000 images, and in the testing set, you have 10,000 images. So that is why you have actually total number of images is basically 60,000. Fine. Then if I just have to show you that how these particular images look like, 1 second. How these images basically look like. So from here, you can see that this is the image. So this image is quite blurry. So the naive approach is basically, you can see that image resolution is very poor, 32 by 32 image. So obviously the resolution would be very bad. So from this particular thing, you'll not be able to understand that what is this basically image refers to. If I just zoom it down or like zoom out. So can you tell me that uh, uh, what is this particular object is? Whether you are able to recognize this particular
Frog?
object or not. Yes, this is a frog. So if I just zoom it down, then you'll be able to understand. Otherwise, if I have to zoom it up, then it is pretty difficult to understand that this particular image belongs to which of the category. Okay. So this is the
Sir,
method.
why is it
So
so?
yes.
Why is it so? Is it due to the magnitude and phase of the like this
No,
graphic or image,
no, this is
or due to the
basically
resolution?
this is due to the resolution. They have given very small images, 32 by 32. In any general images, you see the image like the standard size is basically 2 to 4 cross 2 to 4 cross 3. However, over here they have given only 32 by 32 by 3. So the image resolution is quite poor. So that is why you're not able to understand that which particular class it belongs to, because the images are very small images. So the resolution is quite poor.
Okay, sir. Thank you.
So this particular method was to use Pytorch, and how you can use Pytorch to load the dataset. So this is the standard way using Pytorch. So same way you can use Keras as TensorFlow Keras as well. So initially in around 2016 or something, TensorFlow and Keras, these two were different distributions. Now TensorFlow and Keras have been merged from, let's say, 2019, I think. And now you can interchangeably use TensorFlow and Keras. So there is no issue with that. Previously, if we have to use Keras, explicitly we have to write some scripts for Keras. And if you have to use TensorFlow, we have to explicitly write. But now they have merged with each other. Okay, so if I have to use TensorFlow to load any sort of data set, so I'm using MNIST dataset for TensorFlow. So I'm importing TensorFlow as TF. Then again, Matplotlib, PyPlot, NumPy, these are pretty standard, we have discussed. And now, if I have to import CIFAR10 dataset and MNIST dataset, what I have to write is basically from TensorFlow.keras. So that is what I was saying, that TensorFlow and Keras now they have merged with each other. So from TensorFlow, you go to Keras. From Keras, you go to the inner package called dataset. And from dataset, you are importing the sub package that is basically the CIFAR10 dataset. Similarly, from TensorFlow Keras dataset, you get the MNIST dataset. So if I just run it, it will first import TensorFlow and it will subsequently do the other jobs. Now we have loaded the MNIST dataset. Now I need to extract the training and testing folders. So likewise, in case of in case of Torch, we used these sort of mechanism, like from train dataset is basically referred from this particular thing. So dataset is basically the object, and from that object we are referring to CIFAR10 dataset. So that is why I previously also I told that in case of Pytorch, you will see some sort of object-oriented programming. So over there, you have to define objects and basic OOP structures like C++ or something or Java. Over here, it is quite sequential. It is like a majority of the codes you'll see like C programming की तरह ही दिखता है यहाँ पे. So over here we are using this MNIST object, and then load data is the function that you have to call to load the data set, and it will give you the training images, training labels, test images, and test labels. Yeah. So this particular MNIST data set comprises 60,000 images in the training set and 10,000 images in the testing set. And these particular images are of shape 28 by 28. Even the dimension is now, you can see the dimension is quite lower than the CIFAR10. So that means image resolution is not that good over here as well. And if I just show you that how this particular image basically looks like. So you can see that this is an image of 4. And you can see that it is quite bloody. So the image resolution is not that good. Okay. So this is a custom function to plot 10 by 10 grid. So I want to plot 100 images. So there will be 10 rows and 10 columns to place all those 100 images because 10 plus 10 is 100. So I just run it. It will show me different images, randomly taken different images. So you can see that this is what this particular data set basically looks like. If I just scale it down. Yeah. So it comprises the images of 0 to 9. Similarly, if I just have to load the CIFAR10 dataset, I can use the CIFAR10.load data function to load the data using TensorFlow. So over here also you can see that this is a standard dataset. So you'll see, irrespective of whether you are using Pytorch or whether you're using TensorFlow, you'll see the data distribution is same because this is a standard this is a standard data set. So the training data set has 50,000 images of shape 32 by 32 by 3, and the testing image is also having testing images are there, 10,000 images are there, which is of shape 32 by 32 by 3. And the label names I have given over here, there are 10 classes: aeroplane, then you have automobiles, then bird, cat, deer, dog, frog. So frog image already I have shown you in Pytorch example, and horse, sheep, and truck. So over here also, if you just want to see one of the images, so see, this is the image of a truck. Again, the image resolution is quite poor, but if you see the 10 by 10 grid, so there you'll see all the images will be miniaturized, and then somehow you'll be able to understand that what are the images look like. So this is a frog. If you have seen this particular frog in only a single image, so instead of having 10 by 10 grid, if you are plotting this particular frog solely, so you'd not be able to understand whether this particular image is belonging to frog or not. For example, this is a cat. So this is also a cat. So the image resolution is quite poor. But these are the standard data sets, and we can use this data set to create any sort of machine learning algorithms. And later, if you want to use for your own data, you just have to change the data and your model is ready. You can train your model and you can get the predictions. So these are kind of like hello world problem to machine learning community. Okay. So as we have discussed that how to load this particular data set, we have now done with the loading of the data set. The second important thing is basically we want to extract features from these particular data sets. So for extracting the features from images, you will see there are n number available. So you can extract the energy of the image or energy of the pixel values. You can use histogram. So there are different concepts are there. But as because this is not a computer vision course, this is purely a DLML course. I just have taken two basic features. One is basically the local binary pattern, and another is basically the filter based features. In case of filter based feature, you know that, let's say, if I just give you the intuition, I'm not going into the proper mathematics of that. Let's say you have a signal. So signal is 1D, images are two-dimensional data. So you can just think it of from 1D to 2D. You can just intuitively understand. So let's say this is a 1D signal and its frequency response. So this is with respect to time. The y-axis is amplitude. If you convert into frequency domain through Fourier transform, so over here you'll get the magnitude, or let's say power, and in this particular direction you'll get the frequency components. Let's say it has frequency components like this. Let's say this is 1 Hertz, this is 2 Hertz. So if you want to apply any sort of filter, let's say a filter looking like this, which has a cutoff frequency from 2 Hertz to 4 Hertz. So what will happen if I just pass it through a band pass filter of 2 Hertz to 4 Hertz? What will happen?
Signals tend to be more closer towards each other.
Now, in terms of the frequency content, can you tell me that you have a frequency? Let's say originally the frequency was ranging from 0 Hertz to, let's say, 6 Hertz. Now you are applying a filter, band pass filter, which has cutoff frequencies 2 Hertz to 4 Hertz. So what would be the function would look like? What does band pass filter do?
It will cut out the section, like
Yeah, it would.
where there is
Yeah,
two hearts.
yes. So this particular filter will be applied on this particular frequency response. Then it will only pass from 2 Hertz to 4 Hertz. Rest of the things will be chopped off. So you'll only get the frequency contents from 2 Hertz to 4 Hertz, which is something like this. So from this, you can see that initially you started with this particular representation. Now you are extracting a feature. So this you can call it as a feature. So if you are interested to look at 2 to 4 Hertz, so you can see that this is the feature pattern that you can get. So in case of images as well, you'll see there is an image of, let's say, the frog image that you had seen. If you pass this particular frog image through the, sort of a Gaussian filter, so this is a Gaussian filter. So you'll see that some part of this particular frog image will be highlighted. Some of the part will be with of lower intensity, because it is trying to extract those components which basically resides into the cutoff frequency of the filter. So I'll show you that how it basically looks like. So over there, mainly you will see the striations. So in any standard computer vision application, you'll see that these sort of features are basically used, or any image processing applications. So if I just use a basic standard image, so this is an image taken from the CIFAR10 dataset. This belongs to the class truck. So I'll be using this particular image to initially show that how the features basically looks like. So over here, so this was a RGB image. That is why you basically see the colors of the images. In majority of the cases, you will see most of the features will act upon on the grayscale images. So that is why what I am doing is basically, initially we had this 32 by 32 by 3 dimensional image. So I am converting that 32 by 32 by 3 into 32 by 32 by 1. So if I just have single channel, the RGB image will convert to grayscale image. So that how I am doing that. So over here you can see that I am extracting the 3-channel image. So from the train image set, I am extracting the index 2 image. So this is 3-channel. Then I have to convert this particular 3-channel into grayscale image. That means which has, so over here the shape is, over here if I just write, shape is 32 star 32 star 3. So to do that, what I have done is basically gray image is equals to TF, basically TensorFlow dot image. So now I have to do the vision based application. That is why I'm going to the TF's image library. And from there is a function that is called RGB to grayscale, which inherently converts a RGB image to a grayscale image. And the argument is basically the 3-channel image that we have just currently extracted. So the output would be 32 cross 32, yes, cross 1. Sorry, cross 1. Now, in case of Python, you'll see that there are different sort of data structures are there, or data types are there. So you have to aware about that what sort of data structure or data type that you are currently handling with. So for example, if I just cut out this section and run it over here, let me show you that what is the type of what is the data type. Gray image. So you can see that the data type of this particular variable is TensorFlow Python. Basically, it is a tensor. The last one is basically the type of the data. So this is a tensor data. Now, if I do the, let's say, where it is, yeah. If I do this operation, just hold on for a second. Or I can run it over here as well. Yeah, so over here, you can see that I extracted this gray image from here. I extracted this gray image from here, which is of type TensorFlow, so of type tensor. But over here, when I'm using that gray image and when I'm running this particular function, you are getting some sort of a error. So why this particular error is coming? So over here, you can see that normalize convert to UINT 8. So UINT, it is trying to convert into UINT 8. And at the same time, the data structure is basically, or the data type is basically tensor. However, depending on the library on which you are working, so this data set I was extracting from TensorFlow library. But for feature computation, I am using SK image, that is the scikit-learn library. Scikit-learn library works on NumPy data or NumPy array. And our data is a TensorFlow array. So if I use TensorFlow array on SciPy or this scikit-learn image library, it would throw me an error. So for this, you have to be aware of the fact that what is the data type that you are basically dealing with. So what you have to do, this tensor data, you have to convert into NumPy array, and then that NumPy array can be used with the SK image so that you can get the feature computed. Because SK image works on NumPy array, it does not work on tensor based arrays. So you have to convert the data type. So that was the main goal to basically illustrate. So if I just show you, we had the original image, which was 32 by 32 by 3. Now it is 32 by 1. So you can see that the colors have been flashed out. And now if I just try to extract. So from this particular function, I am extracting the local binary pattern. So this local binary pattern can be extracted with these sort of parameters. So there is a function, you have to pass an image and you have to say that how many vicinity points that you will be working with. So this is the endpoint and uh, uh, radius of the neighborhood. This basically gives you the feature. So this is how the feature looks like. So you had a image, and from this image you are getting some sort of a stridation based features. So it seems like apparently what basically it looks like, it's just like garbage only, but this has some sort of a discriminative properties as well, so that we can extract from histogram. So histogram is basically it gives you the probability of occurrence of any pixel value. Let's say you have a pixel value strength of 1. It basically tries to see that how many time 1 basically appears in the image, or the pixel intensity appears in the image. And then it gives a probability distribution. So to extract histogram, we have used the np.histogram, and then we have passed the LBP features, that is the local binary features. And I have used the bin of 10. So bin of 10 basically divides the range. We have the image intensity range 0 to 255, as because we already told that grayscale image, the intensity level of a grayscale image basically starts from 0 to 255. So from here, so this is the histogram that basically looks like. And from this histogram, we can calculate energy. So energy basically means if you have these, the histogram over here, if this is the histogram, these are the values, let's say 1, 2, 3, like that. So what you can do is basically summation of x of n square. So it is basically 1 square plus 2 square plus 3 square, like that. So this is called the energy feature. Similarly, you can calculate entropy features as well. What is the formula for entropy? Yeah, what is the formula for entropy? The entropy formula is of negative summation of x into log of x. So it is basically, if I just brought it down mathematically, it would be 1 into log of 1 plus 2 into log 2 plus 3 into log 3. So I have taken the values 1, 2, 3 such that I can write it in a simple form. So whatever maybe value you have, that value is actually, you have to put it over here. So these are the equations of the features. So we can use these equations. So we can use these equations and then actually we can. Okay. So similarly, I told about the filtering process as well. So filtering process, what it will do, it will pass the image through a filter, and then it will try to extract some features out of it. And this Gabor filter is basically its equation. It's like this. If I just give you the basis function equation, it is like e to the power j theta. So e to the power j theta, if I just decompose it, it will be cos theta plus j sin theta, right? So e to the power j theta. So these cos theta plus j sin theta, you can see there is a real part and there is an imaginary part. And the filter is basically of this sort. It contains the real components as well as imaginary components. So if you pass an image through e to the power j theta like filter, it will give you two parts. One is real coefficients plus j into imaginary coefficients. And you can extract the modulus as well. So that is basically root over real square plus imaginary square. So over here as well, you can see that this part is the real image. This part is the real features. this part is the imaginary features, and this one is basically your magnitude. So this is where I have written np dot square root. That means it is basically a square root of the real square and the imaginary square. So that is what we have written over here. That is root over real square plus imaginary square. So this is what basically the magnitude spectrum looks like. This is the imaginary part, and this is the what you call the real part. So this is this particular thing I have shown for a single image. Now you can understand that you have 50,000 images. For 50,000 images, you have to calculate all these sort of features. So you have to incorporate, you have to write a loop which will run for these 50,000 images, and it will store these particular feature values over there. So this is why I have captioned over here generalizing features for all the images. So again, let us just load the MNIST data. So MNIST data, we can see that this is for the training part, this is for the testing part. And let me just skim through this particular thing, that what I have written. So in this particular snippet, I have written the feature extraction part for all the 50,000 images in the training set or in the testing set that you can acquire with. So class level, we know that the class levels are being stored in this Y-train and Y-test part. So in case of supervised learning, you need to have the feature values, you need to have the labels as well, so that you can train a machine. So like it is like, given these sort of features, this is the label. Given these sort of features, this is the class occurrence label. So over here, this is class level, and we are extracting total 4 features. What are those 4 features? One feature, one pair of feature basically coming from the local binary pattern, the energy and what you call the entropy. Similarly, the second pair of feature is basically coming from the Gabor filter. So you do the Gabor filter, you take the magnitude, and then you can also compute the energy and as well as the entropy. So these are the 4 features that we are calculating. And so we are calculating, just tell me that we have for one image, we have 4 features. And we have 60,000 such images in the training folder. So what would be the shape for if I just extract features for all these images? So what would be the shape? What would be the dimension?
240,000 features in a total.
Yeah, 240,000 in total, but it is like, you have to tell me, like for one, it is like 1 cross 4, because for one image you are getting 4 features. So for 60,000 images, you have 60,000 cross 4. It is like you have said it correctly, but when you start implementing these things in Python or MATLAB, you should tell me in this fashion.
Okay, sir.
Okay, so this is what you will see in the result of the code as well. So this is the convention that you have to follow. In any sort of ML or DL application, you will see that the data dimension, understanding the data dimension is quite important. So that is why I am emphasizing on these facts. Because you will not be using these algorithms on these basic data sets. This is just to get the things done on the basic data set. So that is why your shape of the output should be 60,000 cross 4. But as because currently I'm not interested in extracting for all the 60,000 images, I just have restricted myself to calculate features for only 2,000 images. Because for 60,000 images, if you calculate these features, it will take around 10 to 15 minutes. So just to avoid that particular time, instead of taking all 60,000 images, I have considered only 2,000 images. But at your own side, you can compute for all the 60,000 images. So that is why you can see that train features, initially I'm declaring a all zero matrix. So which is of shape 2000 cross feature length. So that means 2000 cross 4. However, you can replace 2000 by xtrain.shape0. So xtrain.shape0 basically this is your xtrain.shape. If I just show you, this is xtrain.shape is basically 60,000 cross 28 cross 28. If you take the 0th element, it will give you 60,000. So if I just run it over here, so it would be 60,000. And if you just put this xtrain.shape0 in place of 2000, it would be the shape of the features will be 60,000 cross 4. Okay, then I'm using the loop and I'm using TQDM just to show that what is the progression of the loop. Then what I am doing, for each iteration, I will extract one image from the training data. Then I will convert into NumPy array, as because I told that the library that we are extracting the features that works on NumPy arrays, that does not work on tensor based arrays. So I'm converting into NP array so that I can do the computations. Then this part is for the LBP, that is local binary pattern. Already we have seen that we have to extract the local binary pattern. Then we have to extract the histogram. From histogram, we can get the energy and we can get the entropy. Same as for the Gabor filter, we have seen that we can get the real and imaginary filter outputs from the Gabor. Then we can take the histogram, we can take the magnitude. So this is a square plus b square, and we are taking the mod of 2. And then we are taking the histogram. Then after taking the histogram, from histogram we'll get the probabilities, that is what is the class occurrence or what is the pixel entity occurrence. And then we can extract the energy and entropy. So all these things we have done previously, but that was for a single image. Now we have to scale it up for all the images in the data set. So I'm just stacking all those things over here. And then we have separately extracted the LBP energy, LBP entropy, Gabor energy, and Gabor entropy. Now we have to concatenate all these things into a single matrix. So therefore, or a single vector, so to say. So therefore, I'm using concat features and I'm using np.concatenate. So I'll just remove this. Yeah. So np.concatenate. So I'm concatenating the LBP features and then I'm concatenating the Gabor features in the axis 0. So that means I'm concatenating them in row wise. In case of Python, you will see axis 0 convention is for row. In case of column, it would be axis 1. So this is the convention in Python. In MATLAB, it is something else. And then I am putting all these features, all these concatenated features in each of the rows of the train features, which I had declared with all 0 values initially. And also I am storing the class labels. And I'm appending the class labels one after another. So that means for first image, if it is belonging to class 0, so the class level would be 0. Then if the next image belongs to class 2, so the label would be class 2, which is appended below 0. So it would be 0, उसके नीचे होगा 2, उसके नीचे होगा 3 if the next one belongs to class 3, like that. So if I just tell you that in case of MATLAB, if you write something like this, if you declare an empty matrix, in case of MATLAB, you'll get a data type of array, which is same as NumPy array. If I just have to do some sort of analogy in between MATLAB and what you call Python, if you declare an empty array in MATLAB, it is of data type array, which is same as ND array or NP array in Python. But if you declared the empty array in case of Python, so like this, it would not be array data type. Rather, it is of list data type. So when you are working with Python, and machine learning, so to say, you have to be aware of arrays, list, pandas data frame, then you have tuples. I think these 4-5 data types would be fine. So that is why in the initial part I was asking that whether you know Python or not. So if you are not accustomed with Python, and if you are willing to learn Python, so I would recommend you to start just knowing about what is NumPy array, what is pandas data frame, what is list, what is tensor, what is tuple. So these would be fine. So these are the common data types that we basically encounter in any MLDL application. Then we have converted the train, because this particular thing class level is list data type, and we know that majority of the Python data handling techniques basically work on NumPy array. So that is why I have converted these class labels into a NumPy array through this particular function in Pytorch array. So if I just run it, it will. Yeah, so you can see the feature shape is 2000 cross 4, as because we have extracted features for 2000 images, and the label shape is 2000. So if I just show you the type of class label, the data type, this is type class labels, you'll see that this is a list. However, if I show you the data type of train label, so it would be NP array or ND array. Yeah, so it is numpy.nd array. Okay, so the next, so this is the sequential part. You have to load the data set. We have done this part. You have to extract some features from the data set. We have done this part as well. Now, if you want to save the features into your disk, because you can think that whenever you are coming to this particular what you call the notebook, and if you are trying to extract the features, what you have to do, you have to run this particular snippet again and again. You have to run this particular thing again and again, and that too for 60,000 images, which is pretty time consuming. So to avoid that, what we basically prefer is to save the data. So to save any sort of data or any sort of Python data, you have different bunch of libraries to work on. Let's say you can save data in text format, you can save data in mat format. What I basically prefer is pickle format. Pickle format explicitly reduce down the size of the file. Let's say if you are saving a data in text format, which is of shape, let's say 1 GB, pickle, what it will do, it will compress it down to, let's say, around 550 GB. So it is a pretty huge compression. So disk maybe ye zyada space nahi lega. So over here, how to save the pickle file, how to save it in a pickle file. So for that, I need to import the package called pickle. Then I'm writing a custom function. So that is def. So def is basically to declare any function. So this is definition. Then the function name is pickle save. And the arguments of the function is basically where actually you want to save the data, whether it is in the content file or it is in your drive as well. So you see, I have not shown you. So there is a functionality in Google Colab, that this one, this is called mount drive. I don't know whether it is visible or not. So this is called mount drive. So what it basically does, it connects the Google Drive with you. It connects the Google Colab with Google Drive, so that if you have any data stored in your drive, in your personal drive, you can fetch the data from Google Drive and you can load it in the Google Colab. So this is quite pretty useful, because you can think of, let's say you have a data set and you have stored in Google Drive. So you can mount, you can basically try to make a bridge connection in between Colab and in between Drive, and you can basically fetch the data from Drive to Colab. So currently I have taken the base location as content. So content means this is the content folder. So this particular folder is content. And then I am saving the features in base location plus training features underscore 2k. So I'm naming this particular folder as training features 2k. And the labels also I am saving in the same location with the name as train labels 2k. And if I just if I just do the pickle.dump means it first tries to create a container and then it dumps the file into that container. And then this out file.close, if you have dumped the file and then if you close it, the container will close and then your data will be saved. So this is the process how you do. You first declare a container, you dump the data and you close the container and then you get the file. So if I just run it, you'll see if I refresh it over here, yes, you can see that the files have been stored and you can see the size as well. If I just hover around, yeah, so the size is 62.65K. So the font is quite small. I don't know whether it is visible at your side or not. At the same time, now you have stored the data. Yes. Yes.
Then while we dump the data from the container and then close it, so while we are closing it means that we are setting we are cutting off the connection from that container, isn't it?
Yeah, so at the time of saving, so you can think of like you have a open container, you have dumped the data, you have to close it because otherwise what may happen is through some, let's say you have written some other snippets as well. And by mistake,
Okay.
on the same path, you are trying, by mistake you have done this, let's say on the same path, you are trying to dump some another data. So what would happen? Your container is open. So you have this particular
It
data.
will.
On top of that, another data will sit. So this may create some confusion. So it is better to close that container. So that is why we do this.
Okay.
Okay. So the next point is you have saved the data. So one might ask me that, okay, I have saved the data, how to load that data? So to load the data, I have written another function. So that is called the load pickle file. So you just have to put the name of the file. So over here, our name of the file, let's say is train features underscore 2k. I have to open this particular thing. So it will start like this. It will pass it through a open function. So it would open this thing. Then it has opened the container. Then it had picked up everything from that particular container. So which is basically stored in WGT. And then it had again closed the container. So now the container is open. So if you just pass it through and your data has been now retrieved at WGT, so your return function will give you WGT. So where the data has been now retrieved. So if I just run it, so I have run this particular thing and I'm storing the data in array from pickle. And if I just have to show you that I am getting the same dimension or the same data, so you can see that the data dimension that what I had stored, the feature shape was 2000 cross 4, and again I am loading that particular feature only. So this is of same shape. So you don't have to worry about whether I'm having any sort of data loss or something like that. So there is no data loss apparently. Just for your another reference, you can store the data in text format as well. So you can do np.saveText. Then you put the file name, let's say my feature .txt, as because we are saving it in the text format. So the extension is txt. And then you write, let's say, yeah, train features. So if you run it, if I just update it, so you can see that my features.txt has been stored. And you can also download this particular thing so that it can be stored in your local disk as well, or in the PC as well. Fine. So this is what the dataset loading, feature extraction, and feature saving basically looks like. So next, part is basically after extracting the features, we have the features, we have the labels. Now the thing comes the deep learning and machine learning part, where we try to create the neural networks or the models, which will basically act as a classifier or regressor depending upon your task. So for that, I have not used these features because I had to compute the feature for 60,000 images, so which was pretty cumbersome. So instead of that, I have taken a problem which is basically ECG classification. So ECG is basically the electrical response of heart. There is synoatrium node in heart, so it basically creates electrical pulses, and then the pulse is basically goes through the septum, interatrium septum. Then you have, so this is the interatrium septum. Then you have intra ventricular septum, and then the pulse basically goes like this. It starts from here, it comes here, then it goes here and here in these two directions. So these pulses basically this particular pulses in heart due to synoatrium node creates a graph like this. So this thing is basically called this part is called P wave, this called Q wave, R, and then S, and this is called T wave. So P, Q, R, S, T, these are the complexes that you can see in the ECG, typical ECG waveform. Now, in case of heart disorder, you'll see that the common heart disorder is called arrhythmia. Arrhythmia is basically, it basically means the abnormal rhythm of heart. Either heart is beating at very quite fast level, or it is basically skipping some beats. So, which is basically a pretty hazardous condition. So we are trying to classify normal beats of ECG and different sort of arrhythmias. Like it could be a ventricular arrhythmia, it could be supraventricular arrhythmia, and it could be atrial fibrillation. So I'm not going into details about that, but you can read about all these things, what basically atrial fibrillation means and all. So this is just to show another application that how you can use different libraries to extract data from website. So there is a website called Physionet. If I just show you, Physionet is a very big website for biomedical data scientists. So Physionet comprises data set of n number of repositories. So you can see all these are the repositories of data. At least it comprises around thousands of different sort of data sets. So what you can also use in your research or in your applications as well. So Physionet, the Physionet website has given its own package. So that is called wfdb. So you can use this particular wfdb function to load each and every data that is there in Physionet website. So this is another application just to show that how you can extract data from website itself. It is not there in the drive, or it is not there in the content folder. It is there in some other website. How to fetch the data from website. So if you just run the pip install. So pip install, basically you are installing that particular library first, and then you are importing that library. And then you try to see that what are the functionalities that it basically comprises. So you can see that it is basically extracting the file number 840, file number 841. So sequentially, it is basically extracting all the files. So it would take around 2 to 3 minutes. So meanwhile, you can, if you have any query, you can ask. Regarding the course or exam pattern, if you have any further queries, you can ask, because it will take 2 to 3 minutes.
Sir, excuse me, sir.
Yes.
Sir, I have one doubt. This Physionet database, whether it contains only one-dimensional signals or images it contains, sir?
Images also it contains. There are some data set which basically are chest X-ray images are also there. So this particular data set, this particular website contains both 1D signals as well as image data sets as well. But the number of image data set is quite less. as you have rightly pointed out, majority of the dataset will be one-dimensional signals like ECG, EEG, EOG, EMG, like that.
Thank you, sir.
And if you want to use any sort of biomedical image data, so there are another websites. If I just show you, one is called like you can search in Kaggle. Let's say Kaggle chest X-ray. You can search. So there you'll see n number of data sets. So like chest X-ray image pneumonia, NIH. This is very famous agency, National Institute of Health, US-based agency. So their data set, so it has several sort of data set, COVID-19, pneumonia, normal. So this is one way. Otherwise, there is another website called ML repository. Yeah, so this is UCI ML repository. So in UCI ML repository, it contains around 50,000 or 60,000 data set currently. So you can get biomedical data set. For example, over here, this is a heart disease data set, X-ray data set. You have plenty of data sets over here, ranging from the area of mathematics, biomedical, power system. Like if you are working on the electrical engineering side, core electrical engineering side, and you are trying to apply the machine learning, deep learning things over there, one pretty naive thing would be in power grids, there are faults are happening. How to understand that what sort of fault is happening, or how to predict that given some sort of previous data, how to understand that at this particular instant some fault may happen, so that you can take preventive measures. So this is a what you call a problem statement. So for those problem statement also, you'll see the data sets are available in this particular website.
Thank you, sir.
Any other query?
Sir, in ND array is for multi-dimensional array.
Yeah, ND array could be, you can declare you can declare 1D cases, then you can declare M cross N cases. Even you can go to M cross N cross Z type things as well. It could be of any shape. ND array could be of any shape. 1 dimension, 2 dimension, 3 dimension. Generally, the notion is basically 1D is called vector, 2D data is called matrix, and if you go beyond 2D, these are called high dimensional tensors. But the data type is ND array. ND array. Okay, so we have loaded all the files from this particular website. So these are the file names 889,890. So these are the patient indexes. If you go to any hospital which has archiving system, so there you'll see that you basically assigned with a number, and whatever test result or whatever report that you basically you do in the hospital, those are electronically saved. So you will not be identified with your name. Obviously, in the ward, you'll be identified with your name, but in general, you'll be identified with your card number or your patient identity number. So that is why you'll see in majority of the medical data sets, they provide 001, 002, the indexes or the patient IDs. So similarly over here, these are the patient IDs, because you cannot disclose the patient identity fully in the website. Then this is just to show you, I'm not going into the detail that the data set comprises the ECG signals of variable lengths, but we want to analyze the signals for a fixed length. So I have considered the time window of 48 samples. So I can just show you that how the signals look like. So you can see that these are the 48-second windows. So this is an arrhythmia case. This is called supraventricular arrhythmia. This is normal case, and this is another normal case. So just a naive question that I want to ask is basically, are these two classes, there are two classes currently, are these two classes have any sort of dissimilarity that you can understand from just visualizing the figures? Is there any discriminative nature is present?
S has less number of frequency as compared to N classes. Like S is only visible there for, I guess, one or two times where the dip is very low. In the case of arrhythmia, I guess.
Huh. So one could be, yes. So that is why you can see that as you are saying that frequency component over here, you can see that there is almost a kind of ascending straight line. If I just approximate it, it is a ascending straight line. However, in case of N, you can see there is a curvature is there. So this adds a frequency component. So this is called the P wave. So this is the P wave of the signal. In case of normal, you have PQRST. In case of arrhythmia, in case of basically supraventricular arrhythmia, you see that the P wave is kind of smeared, or it is like very smooth. So that is why you can see over here the P wave is distinctive. Here also P wave is distinctive. But you can see this is a pretty long area that it basically takes. So over here, the P wave is kind of smoothed. So this is one indication of what you call the supraventricular arrhythmia. So over here we have these many signal, these many files. So we have to extract again features. So we have extracted similar features like those, and we can just, we have extracted for 48-second windows. If I just run it down, so it will say that it is basically processing the file, and we are extracting the same features like entropy, energy, etc. So I'm not changing the features. But the problem is, as in the lecture series also, you have seen that we do talk the good features and the bad features. Now, how to know the good features and bad features? If the feature is not able to classify the signals well, then your what you call your machine learning or deep learning classifier will not be able to identify that whether the signal is coming from a disease case or it is coming from a normal case. So if I just show that in this particular, in these three images or in these three signals, energy, what is your opinion on energy? Whether the energy would be almost same in these three cases or not? If you calculate energy,
It will not be same, sir.
like if I just show you other examples as well. One second. Not exactly same, but they could be similar. So that is the point, because you can see that the signal structure is almost same. Obviously, they could not be exactly point by point same, but over here you can see that they don't have some sort of a discriminative thing. So for example, the pattern over here, only the pattern basically changes. In these two cases, you have this kind of pattern, but the amplitude of this particular pattern is very low. You can see if you start from this zero line, it could be hardly 0.2 or something. Over here also. Similarly, you can see that you may not have this particular peaky nature over here. You have some sort of descending thing over here, but major part of this particular area is having a value around 0.2 or something. So if you extract the value of energy in most of the cases, you will see that it is not able to differentiate based on the energy, because they have some sort of similar nature. Not exactly same, but it would look like something like this. So for normal case, if this is the energy of the normal case, the Abnormal case would look like this. So there would be very little overlap would be there. And whenever you see little overlap is there, your ML model will fail. It just predominantly it will fail. There are certain techniques are there how we can encounter or how we can compensate these issues that we'll see in the later weeks as well. But currently my aim is just to show you that with these features, if you use basic classifiers, so for example, over here, there is another example. Yes, this example, you see these bit types are N and this is S. Are they not looking like similar kind of thing? They have some sort of similar structures.
Yes, sir.
So if you extract the features from these signals, they would be almost similar. Not exactly same, but they would be almost similar. So if you extract such features and if you use ML models or DL models to classify them, then your ML model or DL model will find a very hard time to classify them because your features are not discriminative. So let us now do the classification job. So what I am using a data pre-processing package from sklearn. So in case of machine learning techniques, in the subsequent week, you will see that there is a need of normalization. So I'm not going deep into normalization. So there is a need of normalizing your data. So you can do different sort of normalization called min-max normalization and the z-score normalization. So all these normalization have different properties. So for this particular for current application, I'm using z-score normalization. One naive example could be, let's say, I want to classify based on certain person's income and some other attributes whether a loan should be provided or not. Let's say um, uh, I have two features. One is income and another is age. And the output would be whether loan will be provided or not. Let's say person 1 has income 1 LPA, person 2 has income 1 crore per annum, and person 1 has, let's say, it could be 10 LPA. But age is, let's say, uh, this particular person has age, let's say 23 years, and P2, person 2 has age, let's say 65 years. So when you use these data over here, you can see that you have a very high value, 1 crore. In respect to 1 crore, 10 lakh is very low value. So okay. So in respect to 1 crore, 10 lakh is very small value. So if you are using any basic machine learning classifier or deep learning classifiers are very much prone to take decision based on the high values. For example, if I just give you a very naive example, if I see a person is having 1 crore per annum income, so I can think that I can give him a loan and I can get recovery very well because his income is pretty high. So, and in contrast to that, if I see person 1, I would say that his income is not that great. So I might take a huge amount of time to recover that particular loan. So I may not give him the loan. But the problem is you have to see the second aspect as well, age. Person 1's age is 23 years. Person 2's age is 65 years. Like person 2 like as because he is a aged person, he may die as well. So just by looking into 1 crore big amount, I should not take the decision, and I should not take the I should not compromise with the loan recovery period. If the person is 65 and if let's say he's an aged person, has some sort of disease and he may die, then how will I recover the loan? So taking decision based on the very high value would be would create some sort of a fatal consequence as well. However, we can think that if this person is 23 years and let's say he has no medical conditions and all, so I can think that even if I can take a very longer period of time to recover that particular loan, it would be profitable, because if I take longer amount of time, I can impose more and more interest rate on him, and then I can recover a great amount of money. Rather, if I give this particular person to the loan, I have a equal probability condition that this person may die and I will not be able to recover that particular loan. So biasing towards very big value could be a detrimental decision on the machine learning side. So therefore, we have to do normalization. Normalization, what it does basically, it scales all the value in a certain range. Let's say minimum maximize min max normalization ranges all the values from 0 to 1. All the values would be scaled in 0 to 1, so that your reference level is now fixed. Every person will be seen from level 0 to level 1, and based on that you will be taking the decision. So there is no very huge gap like 1 crore and 10 lakh per annum. So this is why normalization is required. And there are some other aspects as well. So this is a very naive example, but technically there are more constraints are there that you have to think about. Then what we need is basically, as I told, that in case of machine learning problems, you see training dataset, testing dataset. But in this particular dataset, they have not given training set and testing set. So you have to manually do that. And for that, you again have another function that is called from sklearn.model selection. You can do this train test split. So this train test split will basically give you the what you call the training part, validation part, and testing part. And after you segregate all this training, testing, validation, what I'm doing is basically I'm doing the normalization, data normalization. So that is x minus mu, that is mean divided by standard deviation, STD. So for all the data, I'm doing this for X train, X validation, and X test. And then we want to use a classifier, a knife-based classifier that you have learned in the week 2, and we'll try to calculate the accuracy so that we can do from this particular function. So accuracy is basically number of correctly classified samples divided by all samples. So that is what I have written over here. So it will partition the data. So you can see that this number of data will go in the training loop. This number will go in the validation loop. This number will go in the testing loop. Fine. So now we'll be using Gaussian naive-based classifier. So we already have seen that what is naive-based classifier in week 2, lecture number 6. So you don't have in these libraries gives you a very good solution that you don't have to write any sort of code by yourself. You just have to know the proper syntax. Even if you don't know the proper syntax, you just search in internet, you will get to the library. You just copy paste it from there, and then you can do the experimentation. So over here, you get the Gaussian naive classifier. Then you declare it with this GNB variable, because already I told that in many of the cases you will see object-oriented based programming. So this creates an object, and then you try to predict based on the training data and training labels. Okay. So over here you can see that your total accuracy is 77.78%, out of which it seems that, so here is another catch. Your total accuracy for 3 classes, you're getting accuracy of 77.8, 7-8% accuracy. But if you see class-wise accuracy, for arrhythmia class, you're getting 15% accuracy, which is pretty detrimental. So one question is, you have 3-class classification problem as because we are classifying N, V, and S, these 3 bits, normal, supraventricular, and ventricular. So what would be the confusion matrix shape? What would be the shape of the confusion matrix? You have 3-class classification problem. So what would be the confusion matrix shape? Yes, anyone?
Sir, I didn't understand question.
Okay, so if I just show it in the this here, so you are classifying normal, then supraventricular, and ventricular. You have 3 classes. These are the true classes. I mean true labels. You have the training data. This is the training data. You have your Gaussian naive Bayes classifier. So this is the ML model. And you are predicting something. This is the prediction. So the prediction is, let's say,
sir,
y
3
hat.
cross 3.
Sorry.
Sir, 3 cross 3 will be the
Yes.
that
Yes.
matrix.
The confusion matrix would be 3 cross 3. So it would look like this. So this side will be actual. This side would be predicted. And this is NVS or like NSV, whatever format that you have saved with. And this is the predicted side, NVS. So this is a 3x3 confusion matrix. Yes. So now we want to see the confusion matrix. How you can plot the confusion matrix? Again, there is a function in sklearn. So sklearn.matrix import confusion matrix. So this is the function that you have to call. So CM is basically the confusion matrix. So in between which of the quantities I have to calculate confusion matrix, I have the true labels y and I have the predicted labels y hat. I have to use these two to create the conf mat. So that is why you can see that confusion matrix takes 2 arguments, that is the test or the original labels and the predicted labels. And I have stored the data in NSV format. So I want it to be plotted in NSV format as well. And there is another concept called normalized confusion matrix. I'll tell you that what is normalized confusion matrix. So if I just plot them, okay. So you see, this is the original confusion matrix. 20928 is basically, this is the true positive, right? These are the true positives. These diagonal elements are the true positives. And you can see that in normal case, you are able to classify it very well. So you can see that 86% you are able to classify. But over here, in case of, let's say, these arrhythmia cases, which are S and V, you are not able to classify well. Rather, you can see that majority of the arrhythmia cases, you are classifying it as in the normal cases. So what sort of errors are these ones? True positive, false positive, what are these? Your original label is S. You are predicting most of them as normal. So what you are encountering over here? False positive or false negative or whatever it is.
False positives.
Yeah, so this is called false positive. So that means you can see that if you try to calculate the classification accuracy roughly, you can take average of these 3. Okay, so 0.86, 0.2 and 0.9 0.097. If you take average of these three, you are getting around 78% or something. Yes, around 78% or something. So this is based on total confusion matrix. This is based on total confusion matrix. So you may think that, okay, I'm getting 78% accuracy. That means I'm doing very good job. But if you see the confusion matrix, then you see that you had to classify the S labels or the arrhythmias as well, but you are not doing the arrhythmia classification very well. Most of the arrhythmias are also classified as the normal classes only. So that means you are doing some sort of misclassification and you are encountering so much of false positive cases, which is pretty detrimental. So you have to analyze when you do evaluate your model, you must have to see the confusion matrix, and from the confusion matrix in the last class I told you that how you can extract the accuracy, sensitivity, etc from the confusion matrix from a multi-class perspective. So you can do the same using this particular using the left side confusion matrix as well. So this is the whole number based confusion matrix. This is the normalized confusion matrix. So how you can do the normalization? You take this, it is just like, let's say you have P1, P2, P3. So if you want to normalize this particular cell, it would be P1 divided by P1 plus P2 plus P3. Similarly, if you want to normalize this one, it would be P2 divided by P1 plus P2 plus P3. So each of the element would be divided with the sum of all elements in the row. So that is how you will get the normalized confusion matrix. So from there you can see that normal class you are able to classify it very well, 86% classification accuracy. For supraventricular you are getting 20% classification accuracy. Over here less than 1% classification accuracy. So that is why if you do the average, you see you are getting 15% classification accuracy in the arrhythmia, total arrhythmia class. So that means your machine learning classifier is not able to classify well. It is not doing a great job. The reason behind it is not doing the great job is basically the features that you are using. So that is what I said. The feature that you are extracting, the energy and entropy from all these bits, you can see that the bit structures are almost same. So the features will also look same. So that is why your model will get a hard time to classify. So we'll see in the subsequent lectures how to deal with such problems, and even in these cases as well, we'll be able to classify it with a very good margin of accuracy. But for those things, we need more mathematical development and more deeper investigation into deep learning and machine learning architectures like support vector machine, random forest, then comes the convolutional neural network and other things. So this is as far as the machine learning part is concerned. So this is the workflow. You load the data, you extract the features. If you want to save the features, you can save it. As if it is not required, you don't save it. Then you create the model, a machine learning model. You feed the training data into the machine learning model, and then you train the model. So for example, over here we have trained the model. gnb.feed basically train the model. Then what you do? You do the prediction based on the test data. And after you get the test outputs, you try to plot the confusion matrix. And from confusion matrix, you try to evaluate that how you have performed, whether you have performed very well or you have done sort of misclassification or not. So this is the proper workflow in any machine learning, deep learning problem. I hope through this particular simulation thing, it is quite like lucid to understand that how the machine learning workflow basically works with. So you can use this particular flow in any sort of your own application, and then you can get the things done. If you have any query, you can ask.
Sir, what is false negative and false positive? False negative is like true value.
Yeah, false positives are, for example, if I just, let me see whether I can copy this to here or not. Okay. So this side is true or actual, this side is predicted. I hope the font is visible.
Yes, sir.
Okay. So this side is actual, this side is predicted. And I can also write these things over here as well, these labels over here as well. So let us now talk about class N. Class N. So when we talk about class N, our true class is N, and false classes are S, V. Now let us try to find what is true positive. True positive means your true level is let's say your true level is N and you are predicting it as N. So that means this is the true positive. So over here your true positive is 20928. Then we have to find the false negatives. False negative means your true label is N, but you are predicting as either S or V. That means you are predicting the negative classes. That is why this is false prediction. And what sort of prediction you are doing? You are doing the negative prediction. That is why it is called false negative. Your original level is N, but you are predicting it as negative classes. So that means the prediction is called false negative. Now you see from the confusion matrix, your original level is N. You are predicting it as S and V. So these two are the false negatives. So your false negative would be 2011 plus 1279. Fine. Now let us talk
Yes,
about
sir.
false positive. False positive means your true label is either S or V, that means the negative class, but you are predicting as the true class, that is N. So what I have written is your original label is either S or V, which is the negative classes, but you are predicting it as N, which is the true class. So that is why your prediction is again false. And what you are predicting it as the true class, that means the positive one. So that is why it is called false positive. So let us see, your original level is S and V, but you are predicting it as N. So that means these two are the false positives.
False
F3.
positive. Yes, sir.
So this is 1346 plus 1185. So this is how you get the false positive. And lastly, you have left with true negatives. So in true negative, your original label is negative class, original label is negative class, and you are predicting it as also in the negative class only. So you see that your true level is S and V, which are the negative classes, and your predicted level is also S and V, which are the negative classes. So what are those cases? So these are the cases.
Sir.
So this is called true negative. So you add up all these values, you will get true negative. So this is when you consider class N, the same true TP, FP, FN, everything will be changed when you talk about class number S, because then your true positive will be this one, because your true level is S, you are predicting it as S. Then your false negative would be these two, false positive would be these two, and true negatives would be these one. So this might sound confusing, but you can do it class-wise, and then you can get all the accuracy measures like accuracy, sensitivity, specificity, etc.
Yes, sir. Thank you. Yes.
Okay, so I will share this particular code in, I will upload this in my GitHub profile, and uh, I will link it in the Q&A part as well. In the last week as well, you see that I have posted the message. So this week also I will upload the video, and I will upload the G Drive link of the slide, as well as I will also link my GitHub profile from which you can download the code and you can run it at your end. So as because in this particular week, I have not dealt with any mathematical problems. In the next week, I will deal with the mathematical problems because I created the slides anyway, but now the time has exceeded anyway. So these are the problems that I will discuss in the next class. Seems that there are no further queries, so we can end this session.